Good afternoon, everyone, and thank you for attending this talk. First, I want to thank the organizers for inviting me. It's a pleasure and an honor to speak here at EuroS&P. I will talk about microarchitectural security, and more specifically about programming language-based methods that can be used to study microarchitectural security. I chose this topic because I believe it will be an important area for years to come. My objective is to kind of give you an understanding of the current state of the art and some of the open challenges in that area. The talk will be directed towards a broad audience, so you don't have to be an expert in microarchitectural security to follow this talk. At least that's what I hope. Ask me questions if anything is unclear, of course. And I should start with a disclaimer. I have worked in this area, but what I'll talk about here is the work of many people. So it's not because I talk about something that I claim that I've done this in any way. I'll try to give references of the papers that this slide is based on along the way. So what is microarchitectural security? Well, this is important in settings where different stakeholders are running software, are running programs on the same platform, on the same processor, let's say. And the code of these different stakeholders is isolated. We use mechanisms like process isolation, virtual memory, virtual machines to isolate the code of the different stakeholders, but they do share some what we call microarchitectural resources in the processor. Things like caches, branch predictors, typically features added to a processor to improve the performance of the processor are shared between the software of these different stakeholders on the same platform. And that leads to certain security issues, and that's what microarchitectural security is about. So this has been known for quite a while, and it's been relevant for security critical software for at least 15 years. So the crypto community has understood this for a long time already. For example, cache timing attacks have been known for a long time. A good survey on this field, you see a reference to a good survey on the slides. And also countermeasures have been developed for these, let's call them classic microarchitectural attacks. So a very well-known one is the constant time programming model, which is a way of writing software that is resistant to these microarchitectural side channel attacks. And also programming language-based methods have been used to study that. For instance, it's known that you can verify whether software adheres to the constant time property relatively well. Again, relevant reference is on the slide. But about 4 years ago, transient execution attacks kind of changed the game in microarchitectural security. Attacks like Spectre, Meltdown, Foreshadow, I'm sure you've heard at least some of these names before. These attacks showed how speculative and out-of-order execution, these are other microarchitectural features, these features significantly amplify the problem of microarchitectural attacks. And well, it was not just these first attacks, and many other variants followed, and the impact of this line of attacks on academia and industry has been huge. So let me illustrate both points. So first, in terms of number of variants, just to give you an indication of the breadth of the problem, I show you on the slide here a classification tree from the paper of Canella et al. That's further maintained on the web. And I'm not going to go into the details of this classification tree, but I hope I'm just showing it to you to indicate the breadth of the problem. There are many variants of these transient execution attacks, as they are called. So in addition, the impact of these attacks on both academia and industry has been huge. And again, to illustrate that, I show here on the academic side the number of citations of the first 3 papers on these attacks, Spectre, Meltdown, and Foreshadow. Together, even though they're like 3 years old, together they have more than 3,000 citations. I think that shows that there is interest in academia in this field. And on the more applied, on the practical, on the industry side, more than 30 CVEs have been filed in this area. And we've seen over the last couple of years significant efforts by companies like Intel, Microsoft, real technology giants to mitigate these risks. Now, I think looking back over the past 3-4 years, the discovery of these vulnerabilities and corresponding attacks, as well as the development of the first countermeasures, has been productive, no doubt, but it's also been quite chaotic. We've seen academics compete for finding issues first. We've seen companies protecting their customers through long embargoes and maybe quick ad hoc countermeasure development, where the countermeasure is then not always perfect. So of course this was necessary. These attacks came unexpectedly and a quick reaction was necessary. But I think this class of vulnerabilities is important enough to deserve a systematic and foundational study. So we should think now at a more leisurely pace about how should we model processes to reason about microarchitectural vulnerabilities. And I will discuss in this talk one approach, the language-based approach, where we use techniques from the programming language community essentially to do this modeling. And many instances exist, and here are the most important papers that I based this talk on. The list is not complete, as you've seen. There are thousands of papers on these topics. It's impossible to be complete here, but these are really good references if you want to kind of read your way into this language-based approach to model microarchitectural attacks. So for the rest of the talk, what I'll do is I'll first introduce a simple instruction set architecture model, an ISA model. So we'll need a model of how a processor behaves architecturally before we can study the microarchitectural details. Then I'll talk about classic microarchitectural side channel attacks, things like cache timing attacks, and how they were modeled, and that this actually went quite well. And then I'll address the question of how to model these new transient execution attacks and discuss some of the questions and challenges that still remain there. Before we can study microarchitectural aspects, we need a model of the architectural behavior of the process, of the instruction set architecture, or the ISA of the processor. And that's relatively easy to do using operational semantics techniques, classic programming language techniques. So here you see an example of the definition of the syntax of a very simple assembly language, machine code language. We have registers, R0, R1, or we also use more descriptive names for registers when we want to. Values, for simplicity, are just natural numbers. We can compute on these. We also use them as addresses to index memory. We can build expressions on values and registers. And then we have 4 kinds of instructions. Internal computation, where we evaluate some expression and store the resulting result in a register. Memory access operations that transfer values between registers and memory. So the expressions here compute an address, and then the contents in memory at that address is either loaded into a register, or a register is stored in that memory cell. Then we have control flow operations, an unconditional jump to an address specified as a value, and a conditional jump to an address specified as a value, and we only jump if the register is different from 0. And finally, we'll use in some examples an instruction to read the clock of the processor. A program is then simply a list of instructions, and here is an example program, and it should be very easy to read. So this example program, I have the C-like code next to it, computes the sum of the first 2 elements of the array A. The register A contains a pointer to memory where an array is stored. It computes the sum of the first 2 elements of that array. So for instance, if you start the program in a state where all registers are 0 and where memory looks like this, then this would compute the sum 9. We can define the semantics formally of this simple machine code language. Typically, we would do that using inference rules for a small step operational semantics. But I'm just going to show you the example because that's easier to understand. And those of you who know how these rules work can easily, I hope, see that you could easily define them for a language like this. So the program states will consist of memory, which will be just a list of values that we index into with a natural number as an address. A register bank, which is a finite named set of registers that can all contain a value, and the program counter, which points to the currently executing instruction. And then we can define a transition system in the standard way. Here is an example of how the example program we had on the previous slide, how it would execute if we started in this initial state with all registers and the program counter equal to 0. I'm not going to walk you through all the transitions. Let's just look at two of them. So for instance, this load here, that's the instruction that's executed in this transition. We first compute a plus I, which would give us 0. That's an address in memory that we look up, and that contains the value 5, and 5 will be transferred to the register R0. That's the semantics of load, and I hope you see you could easily define a semantic rule for that. Another one that is a bit interesting to look at is the timer instruction that's executed in this transition here. So the interesting thing is, even though the ISA-spec tells us that this reads the clock, the ISA-spec doesn't tell us what the value of the clock will be after executing these instructions. So it doesn't specify the execution time of instructions. So that means that the result of that timer instruction is to some extent non-deterministic, and it's this kind of non-determinism that can then be exploited in microarchitectural side channel attacks to learn something about what's happening on the platform. So at the architectural level, the level that we're defining now, programs are completely isolated, right? So we're reasoning about a platform that runs programs for multiple stakeholders, but these have no influence on each other whatsoever. Attacker and victim program, when they both run on the same platform, would have separate program code, separate memory, separate registers, separate program counter, and so forth. There is no information leak at the ISA level of abstraction. But of course, there will be interaction or information leaks at the microarchitectural level, and let's first look at these classic microarchitectural side channel attacks. So the main reason for the existence of these information leaks is the fact that microarchitectural resources like the cache are actually shared. On this picture here, you see that attacker memory and victim memory, the green memory here, are fully isolated. They don't share anything. There's no memory shared between victim and attacker. However, the cache, which is a small fast memory closer to the processor, which the processor keeps copies of values that will be needed again, or that the processor expects will be needed again, these caches will actually be shared between the various stakeholders. So for example, here we see a simple example of a cache that has two entries. One entry can contain one of the even addresses of memory, and the other one can contain one of the odd addresses of memory. Right? So that means that, for instance, this address of the attacker and this address of the victim compete for this same cache entry. And if the processor wants to put this in the cache, he might have to evict this one. Right? And that creates some form of information leak. It's well known, the cache side channel attacks. And we can model that using language-based techniques. For instance, such a cache with two entries, we can model it with a cache state. That's a pair that remembers the two memory addresses that are currently cached. So one even and one odd address. Of course, it's also possible that the cache entry is empty, and we represent that with the value undefined here. In addition, we'll extend our processor with a clock so that we can do actual time measurements. And so then we get a program state, which is the architectural state, memory, registers, and program counter, and then a clock counter and the cache state. Okay, and here you see an example of such a program state where I will draw the architectural state in white and the microarchitectural state in gray. So here is a constructed example to show you what happens on uncached and cached loads. So the essence that we want to model is that uncached loads will take longer. And the way in which we can do that, one way of doing that is by having an uncached load take 2 cycles and a cached load take 1 cycle. And that's what you see happening here. So when this program starts, we assume the cache is empty. So this will be an uncached load, and it will take 2 cycles. In the first cycle, the corresponding memory address will become cached. And then in the second cycle, the actual load will happen. We see that the value 7 is in the register V. If we then override V and do another load, so if we now do this load, which will be a cached load, we see that this load only takes 1 cycle, because the address we're trying to load, address 0, is in the cache, so we can load it in 1 cycle. And we also see eviction happening. So if later on at this point the processor wants to load from address 2, this will again be an uncached load, and we'll see that first the address 2 will become cached, and in order to become cached it needs to evict the address 0. Right? Okay, so that's kind of the well-known and well-understood behavior of caches. And once we have a model of that, we can actually show how this gives rise to information leaks. Because this cache will be shared between attacker and victim, and because the attacker can influence and observe some aspects of the cache state, we have a communication channel. And here's an example of an attack, a very simple prime and probe attack. The attacker will first make sure that his address, let's assume the attacker owns these memory addresses and the victim owns these. These are architecturally isolated. The attacker first loads one of his odd addresses, so then he knows that the cache state looks like this. Then the victim runs, so this is vulnerable victim code because it loads a secret. Let's assume address 0 contains a secret, and then branches on that secret. So depending on whether the secret is 0 or not, we skip this load or we perform the load. But that means that depending on whether the secret is 0 or not, the cache state will look either unchanged, or the 11 will be evicted and instead address 1 will now be cached. And whether we're in this state or in this state, the attacker can then measure that by timing how long a new load of address 11 takes. So that's the essence of a cache timing attack. Now, unfortunately, this kind of modeling is not great if we want to prove software secure. It's good for understanding how a cache attack works, but it's not great for proving security of software, because if we want to prove something, then we need to model exactly what happens on a given platform, and what exactly happens can be very complex. You have different instruction and data caches. Cache sizes can be different on different platforms. Moreover, it's not only the cache that leaks. There are other microarchitectural elements that can leak information. So one great idea in the development of countermeasures against microarchitectural attacks is to kind of just over-approximate what leaks. So we simplify by over-approximating. So we're just going to assume that when victim code runs on a shared platform, then the entire control flow, so every time the program counter changes, this leaks to the attacker. Why? Well, for instance, because you might be able to learn that through the instruction cache. Also, whenever victim code performs a memory access, we're going to assume that the address of the memory access leaks. Not the value that's being read, but the address that you're accessing. Why? Well, because that's exactly the kind of thing that might leak through a cache attack, for example. Sometimes other things are assumed to leak. I'm not going to focus on that in this talk. But that's a great idea. Why? Because now we don't need to model the details of caches and the details of clocks and so forth, and possibly other microarchitectural elements anymore. We can just stick to the base semantics. So what you see here on this slide is again the base semantics executing the example program we had a couple of slides back. Now what we're going to do is we're going to extend this for each step that the program takes, we're going to admit that certain information leaks. In particular, we assume that in every step the program counter leaks, and whenever we perform a load, the memory address that we have accessed also leaks. Okay, and by just specifying that, we can now define security. So if we have a victim program that has a secret somewhere, for example, it has a secret in address 0 of memory, then we're going to say that the program is secure if for any two states that only differ in a secret, if you execute the program, what leaks to the attacker is the same. So in other words, if the attacker can distinguish two program states that only differ in secret values, then the attacker can learn something about the secret, and that means the program is not secure. So we have a formal definition of security, and here you see it at work for this example vulnerable program. We take two program states, we make them different just in the secret, and we see if we execute the program in these two states, that what leaks to the attacker is different. Right? In particular, in this step, we'll have an access to memory address 1 if the secret was 0, and we won't have that memory access if the secret was different from 0. So the fact that the attacker can distinguish these two executions shows that this program leaks something about this particular secret. Okay, so we have a formal definition of what security means, and it's relatively simple. So this is actually a very influential and successful approach. The state-of-the-art crypto libraries are implemented to be secure under this what's called constant time model, and it's been shown that formal verification of software, whether software is secure under this model, is actually practically feasible. You see the relevant references on the slide. So the interesting question now is, can we do something similar for this new wave of transient execution attacks? Can we do the same kind of over-approximation and simplification and reasoning about software security? So let's build a model of a processor that does speculative execution. I will do this again using an example. So the basic idea of these processors is that they can now fetch multiple instructions and store them in a microarchitectural element called the reorder buffer, and then execute these instructions possibly in parallel, possibly out of order, and then once they're executed, commit them to the architectural state, commit their effects to the architectural state again in program order. So let's see how that happens in this example here. So here we have a toy program designed to show how a speculative execution processor works. So we first fetch the first 3 instructions, for example, and place them in the reorder buffer. So of course we need to keep track of where we are fetching speculatively, and we use a speculative program counter for that. Once we have instructions in the reorder buffer, we can start executing them. And the only constraint here is that we can't execute something for which we don't have all inputs yet. So for instance, we can't compute this expression because I is still unknown, right? And even n is also still unknown. But anything for which all dependencies are satisfied, we can execute. So for example, we could execute this instruction. Right? And once an instruction at the top of the reorder buffer is executed, we can commit it to the architectural state. So we remove it from the reorder buffer and we show its effect on the architectural registers. And then we can fetch another instruction. So in this case, we would fetch the branch instruction. And here something interesting happens. So we're fetching this branch instruction, but we don't know yet whether the branch will be taken or not. Right? We are not that far in execution yet. So the question is, where should we continue fetching? Should we assume the branch is not taken and continue fetching here, or that it's taken and continue fetching here? And that's where, of course, the branch predictors come in. And this processor has a very simple branch predictor that remembers 1 bit. It will predict globally whether branches will be taken or not taken. Okay? And for instance, in this case, the state of the branch predictor says branches will be taken. So then, in that case, we will fetch the branch, change the speculative program counter to 5, but record that we have made that prediction. So in the reorder buffer, we'll say we predicted a branch based on our 0 to address 5 to be taken. Okay, so let's look at both cases actually, where we predict taken and where we predict non-taken, so that we can see both what happens on an incorrect and on a correct prediction. So let's follow first the taken case. If we predict taken, then the next instruction to fetch is instruction 5. So here we fetch that in the reorder buffer. And now we can start executing instructions. So for instance, we might execute this one because all its dependencies are satisfied. And we know I, and it doesn't change here anymore. So we can compute this instruction. And then we might execute this one. And once this is done, we can execute this one. And in a couple of steps, we would end up at this state.
Right? And now two instructions at the top of the reorder buffer are fully executed, so we can commit them to the architectural state and end up here. And here we will now notice that our prediction was wrong. Right? We predicted that based on R0 this branch would be taken, but R0 is actually 0 at this point, so the branch will not be taken. So what happens at this point is a rollback. All the instructions in the reorder buffer get flushed, thrown away, and the speculative program counter is reset to indicate that we were wrong, that we should actually not have taken the branch. Right? So this is interesting. We see here that an instruction was executed. This instruction was actually executed, but never committed to the architectural state. And these instructions we call transient instructions. So they get executed and then squashed one way or another. Okay. What happens on a correct prediction? Well, in that case, we have to continue execution after the branch here. So we keep fetching all instructions into the reorder buffer to get into this state. And then we can start executing, and we can execute this one and then this one, for example, to get into this state. And then we could execute this one and then this one to get into the state that we see here. Now, these two in-flight instructions can be committed to the architectural state. We arrive here and we see that in this case our prediction was correct. We predicted that a branch based on R0 would not be taken, and indeed R0 is false, 0, so it will not be taken. That means that everything we did here was correct, and we can now all commit it to the architectural state, and we are actually done with the program. And so we see in the case of a correct prediction that we can win quite a bit of time. Executions of instructions that we've done here can now quickly be committed to the architectural state. But this optimization mechanism can now lead to new information leaks. There are two issues. First, these transiently executed instructions, so instructions that get executed and then squashed, can also leak information into the microarchitecture, and that might be observable by the attacker. And that's kind of weird, because these are instructions that you would expect not to be executed, and still they are leaking information. A second issue is that sometimes transiently executed instructions can access information that you expect to be inaccessible. That can even be information in other hardware protection domains, like in the kernel or in another process with Meltdown style attacks, and I won't talk a lot about that in this presentation. And it can also be information that's architecturally accessible, so in the same in your memory address space, but that you expect not to be accessible because of bounds checks. For example, you might have software that bounds checks access to arrays, yet speculatively or transiently, arrays might be accessed out of bounds, and that leads to Spectre style vulnerabilities and attacks, and these are the ones we'll focus on. So I'll give an example of the classic variant 1 of Spectre in the model that we defined here. So here is the classic Spectre v1 snippet. We assume in memory that we have a 2-element array A and a 2-element array T, and we assume that the length of A is stored right before A. So what we see in this code then is that we load the length of the array A, check whether an index I possibly provided by the attacker is in bounds. If it's out of bounds, we jump to past the two loads here. If it's inbound, we will perform these two memory loads. Okay. So let's see what happens if we execute this snippet of code speculatively. So let's start in this state. We fetch all the instructions, and now we can start, and because the branch predictor predicts that the branch will not be taken, we actually fetch these load instructions here into the reorder buffer. So then we can start executing instructions in the reorder buffer. For example, this instruction, we know A and we know I, and they won't change here anymore, so we can execute it. A plus I will be 3, so we access memory address 3 and find 1 there and execute the load instruction here. Right? And then once we have done that, we can execute this instruction. We know T and we know R0, at least speculatively, that gives us 5. We access address 5, find 8 there, and execute this load too. Okay. Now, of course, a bit later on, we will discover that actually the prediction of this branch was wrong and we should not have executed these instructions, and we'll squash them and we will do a rollback like we've seen on the previous slide. But both loads have actually been executed. So the effect on the cache has actually happened, and so the memory accesses that have happened will actually be visible to an attacker. And that's the essence of a Spectre attack. So if the out-of-bounds access that happens, in this case to address 3, contains a secret, marked by coloring it red here, then that secret will actually be read here, and it will influence the observation of the attacker here, because the secret is used in the, as an index in the second load here. So what we see is that purely transiently, observations by the attacker can be made that allow him to learn something about the secret. And that's the essence of a Spectre attack. And now that we have a model that can explain these attacks, next, of course, we want to simplify, perhaps by over-approximation, just like we did for cache attacks through the constant time model. And that's what the community, the research community is currently doing, and some very interesting steps have been taken already. So in the first step, Colleghi et al. At PLDI 2020 propose how to avoid modeling the details of predictors or the details of how a processor chooses which instruction in a reorder buffer to execute and so forth. So what they say is we should assume that the attacker has full control over these. So the attacker can provide directives of what predictions the processor should make and what instruction in the reorder buffer it should select for execution and so forth. So these are attacker controlled. And then we should prove absence of leaks for any possible directives given by the attacker. So that's a first great step to simplify what we need to model about the microarchitecture, but we still need to model the reorder buffer. So can we avoid modeling any microarchitectural details? So in Security and Privacy this year, Guarnieri et al. Proposed what they called hardware-software contracts that make full abstraction of microarchitectural details. They're a combination of a leakage model that defines an upper bound on what leaks in computation steps, a bit like what we've seen in the constant time model, and an execution model that provides an upper bound of the computation that could be done by a processor, including transient computations. For example, the speculative branch prediction that we've seen could be modeled by defining an execution model that says that a program will execute both taken and non-taken branches up to a certain depth of any program that the processor executes.
But this research area is still wide open. Many challenges and open questions remain. So I'll just mention 2 important ones here. First, the notion of execution model works very well for branch prediction, but it's unclear how this will generalize to other kinds of predictions. Even prediction of computed jumps, for example, doesn't seem to work well. So more research is needed here. And maybe even more important question is how do we validate proposed models? If you look at the different papers that this talk was based on, the various proposed models differ in the details. Which one is most correct? So when we are given a certain processor, how do we validate that it complies with the proposed model? Both leakage models as well as execution models are very difficult to validate empirically. And without some kind of rigorous validation, why would we trust security proofs based on such a model? So essentially, this is the question of how can a chip maker that provides us some very complex black box, a processor, how can they provide us evidence that that processor has certain security properties, will comply with a given security contract, for example? And that's a very important and interesting question, I would say. So that brings me to the conclusion of my talk. I hope I convinced you that microarchitectural attacks are an important and interesting class of attacks to study. I hope I also convinced you that formal models of processor behavior can help us, both in understanding as well as in improving software secure and thinking about more secure hardware implementations. And the field is still wide open. So if you're looking for a topic to do research on, I very much encourage you to jump into this area. With that, thank you for your attention, and I'm happy to answer questions.